Now, this part of the chapter gets kind of exciting. What we're going to do here, well, I say exciting, you know how it goes. What we get to do here is we get to start predicting what happens when you combine two compounds together. So no longer is it just passively looking at a reaction, you're actually going to get to predict the products of that reaction. Now, today we're going to be looking at what are called double replacement or metathesis reactions. So let's see what those are. So what a metathesis or a double replacement reaction is that we have an ionic compound. We actually have two ionic compounds, and they're going to switch partners. Sometimes they'll talk about how this is like a square dance, or they're swingers, or however you want to think of it, they're going to switch partners. So let's see what that would look like. So we have two compounds. Oh, that doesn't write very well. Let me change colors really quick. We have compound AB. Now, if you look just at compound AB, this is a generic way to write it. A has to be the positive part because it's listed first. So for us, that's going to be the metal. And B is the negative part, the anion. That's going to be your nonmetal. And we're going to react that with another compound. And we're going to call this compound CD. Again, it's just a way that we can generically write this compound. C is your positive part, D is the negative. Now these two are going to react. So the positive, well, the positive of one can't react with the positive of another. So A is going to react with D. And then C is going to come back and react with B. Don't worry, we'll do a few examples of these. But again, we have this, they're going to change partners. We keep in mind what's positive and negative. We have to look at charges. So there's a couple of things to this. Now, with this metathesis or double replacement reactions, there's two main types that we're going to be talking about. One of them are called precipitation reactions, and that's what we're going to focus on today in this lecture. This is where one of your products is something that forms a solid. So we're going to be looking a little bit at solubility rules, and we're going to look to see how to read a solubility table. There's also something called acid-base reactions, and that's covered with another video. So let's look at these precipitation reactions and see what we can find out. Now, over the years, scientists have realized that they can predict whether or not a substance is likely to be soluble, meaning that it will dissolve in water, or insoluble based on just the chemistry of it. So in your book, you have these solubility rules. So it talks about these compounds tend to be soluble if it's a group 1A, or if it has ammonium, or if it has chloride, and these tend to be insoluble. If it's got a phosphate or a carbonate. I won't have you use these rules. These rules are great, but they've actually put this into a table form that's a little bit easier to understand. And I'm actually going to give you the table on the test. So I'm a little more concerned that you can read the table. So let's look at it and see what it has to say. All right, so this is what the solubility table that you're going to use in class looks like. You'll always get the top one. You might not always get the bottom one, but I will give both of them to you on this next test. So what this has, and if you want to find this, there should be a copy listed right underneath this lecture on your Moodle page. So what this has is it has the anion listed. So that seems almost backward. It has the last half of your compound listed. But it turns out that that anion tends to be able to predict whether something's going to be soluble or not. And then it says, okay, if we mix that ion with these cations, it's likely to be soluble. Now, this is a general rule of thumb. Of course, there's always exceptions to this, but in general, if you mix that ion with these cations, it's going to be soluble. But if you mix that anion with these cations, it's going to be insoluble. That means that it forms a solid. Soluble means that it's AQ, that it forms this aqueous solution. Now, sometimes I'll admit, sometimes I'm not paying attention and I say, oh, soluble, that gets an S. No, 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 no. Your solid is what gets an S. That's what's insoluble. So let's do a few examples. So let's look over here, say at chloride. Chloride's one we use a lot. And it says with chloride, most cations are soluble. So chloride likes to be soluble, except, and then it has these exceptions right here. If you mix chloride with silver, with mercury, with lead 2, with copper, with tellurium, those are going to be insoluble. So silver chloride is insoluble. It would form a solid. Now, the bottom part goes through this same type of idea, but it shows it a little bit different. So here's chloride right here. And if it is not shaded in, that means it's soluble. But if you go right here, oh, here's one that's shaded in. That's with silver. So silver chloride is going to be insoluble. So we have it with words, and then we have it down on the bottom with just a little shaded in chart. Again, I like the top one better. So use this to help us predict some things. Let's look at one more. Let's look at carbonates. So with carbonate, it says, all right, if you have carbonate mixed with ammonium or anything in group 1A except lithium, so if you have it with potassium or sodium, it's likely to be soluble. Everything else, it's going to be insoluble. So this chart's going to be very, very useful. One other word of warning, sapling actually has their own chart. I should probably use sapling's chart, but this is what I have right now. So this is what we're going to be looking at on the test. For sapling, be sure to use theirs.